We're starting a new kind of endeavor today. It's been very small atomic structures, you know, things like electron configurations, the periodic table, coordination numbers, and a few other things that we've been doing, you know, trying to get geometries and the shape of things right and stuff like that. A little bit of drawing. It's been great. But it's time to move ahead to larger molecules, and then to even larger molecules that make macromolecules, and then polymers, or biopolymers as people call them. A lot of times you put those into even larger assemblies because it's a long way from atomic scale up to something you can actually build into a product. Some of our learning objectives include understanding the scale of polymer production, which I'm going to do just by sort of showing you some factories and get an idea of how much of this stuff we make, especially considering that we made very little of it as recently as, I don't know, 60 years ago. We want you to know the difference between condensation and addition polymerizations. These have different names now. And everybody in the field is trying to stop saying condensation and addition, but we'll tell you the new names, and you can be on the vanguard of new naming this. We'll try to get you to understand the distributions of molecular weights, because usually when people make polymers, as opposed to nature making polymers, we don't get the same molecule every time. Some are bigger and some are littler. They're all the same kind of molecule. They have the same elements in them in the same proportions, but some are bigger and some are littler. And we have a hard time controlling that. We'll try to make you familiar with some biopolymers, which are very important right now. The whole problem with COVID-19 is one particular biopolymer. We'll talk about that a little bit. Understand absolute versus calibrated molecular weight determinations. Try to do a little bit of that. We'll talk a little bit about polymer phase relations. There are intricate polymer phase relations to be studied here. I'm not sure. Yeah, I think it might be even more complicated than the metal phase relationships. Your book does a bang-up job on metals, but I think it actually claims that there aren't really phase separation things to study in polymers, and that's just not true. So this will be our introduction to phase, and that'll be important for us later on. We'll try to understand stereochemistry of the polymers. In some cases, it really matters. We'll look at two different measures of size. How would you decide how big a polymer is? And you can weigh it and get its mass, but really how physically large is it? We may do a few other things in here that aren't on the list. We're not going to do it all in one day, that's for sure. So I thought we'd begin with just Lewis dot structures, or some simple things. And this will be using these Lewis dot structures to follow how polymers are made. We'll do a little bit more of that than some other groups. It's more than your book. I'll try to do this inside of PowerPoint, and if it misbehaves, we'll switch to something else. So NH3, remember Lewis dot structures, you count the number of valence electrons. So it's 5 valence electrons for nitrogen and 1 for hydrogens. Times 3. So this molecule has this Lewis dot structure. And it's important to remember that spaces aren't what you see. I mean, all the volume of these things is taken up by the electron clouds. So if we try to draw this, in a sort of a 3D perspective, let's see, we'll put the, we'll rotate it, let's rotate it on top so that we have That's not 3D perspective yet, but now we'll make it 3D perspective. We'll put a big cloud, and we'll put a little teeny end there. Okay, that's the end. And then there's this other big cloud, and it's small. The real thing out there, the proton, is really small. And those two are in the same plane. See, I say that these two are in the same plane. Those two define the plane of the screen. And then we have another electron cloud that leads to a proton, and it's coming out. It's coming out of the plane of the screen. So we'll make it a little bit bigger at the bottom, and then this other, the last one, will make, you know. Okay, so these little dots that I'm drawing are meant to be the protons. Okay, except for these two. So maybe I should make these like little stars or something. Okay. So remember that all the mass is incredibly concentrated into this tiny little thing in the nucleus. So that's a Lewis dot structure for ammonia. Acetic acid is a great one. Vinegar. That's a structure we would just write as a line structure for it. If we wanted to give it, actually this thing will exist more or less in 2 dimensions. So we can draw it like, that's, you know, more or less what's going on. If I was being really fussy, I would realize that I'll put this proton here right in the plane, this bond here, and then so those two are in the plane, then this one's got to come out at me. And that one's got to go away from me. Okay, so you see that the carbon is tetrahedral. This bond angle here is maybe about 120. And this bond angle here is not 120, even though it looks like it should be. This is maybe about 109.5 because I haven't shown the electron clouds. When I put the electron clouds in, that oxygen is really at the middle of the tetrahedron too. Okay, but the Lewis dot structure, you know, the one that we really use is simpler than that. For this one, well, I guess we could, if we wanted to expand another, we could do like this. Often we write these in just 2 dimensions, that's fine. I guess if I wanted to be strict about it, I would let those be okay. So the point of doing this is that we're going to be able to show you what these electrons do. These are attack electrons. Like you have like an attack dog or something like that. These are attack electrons. And these ones really are. Oops. These ones are really good attack electrons. Vinyl acetate. We'll do one more. Vinyl acetate is an acetic acid. Now it would be OH if it was acetic acid. It's going to be O something else. It's going to be OCH. CH2. Okay? And so to draw that a little bit better, we could just draw that as, you know, CH3CO CH. This is even, you know, simpler for your typist to do. Back in the days when we had typists, this is simpler to type that out. And as, you know, material scientist, you still need to know how to get from that to the real structure, which is, you know, sort of like acetic acid, but with a different thing. Instead of this proton here, it gets something else. So let's try to draw it. I think we'll go one page and put it up here. So we had it as CH3CO CH2. And the key is that you have to remember that everything wants an octet of electrons. So just like we did before, we'll do a C here. Put that there. Let that be a double bond there. Doot, doot, doot. We'll come down here, and this will be an O. I guess we'll put a C here. H there. And I need my backward one. I need my something like that. So this one is coming out of the plane of the paper. This one is behind the plane of the paper. This one is in the plane of the paper. So they're three-dimensional. And I still haven't got in all the dots. Now I do. Now it should be okay. It's an interesting molecule, this one, because it turns out some of the attack electrons can go here, right? And other attack electrons can go here. So that's kind of an interesting molecule. And an important one for us to understand is styrene. This is another important one for us to understand. And by the way, if you're just sitting there watching me do this, you're not getting anything out of it. You should rewind, get a piece of paper, and follow along, draw them. And if you need to stop, you can stop. Styrene is this molecule. That'll be close enough. And its structure. Is this. I have to remember to put all these carbons in here. We really don't do that a lot. It's tedious to draw all the carbons, and we'll talk about what we do instead of that in a minute. So there, double bond there, double bond there. That's styrene. Very important polymer for all sorts of reasons. It's in styrofoam cups, it's in styrene, SBR rubber, styrene, butadiene rubber, it's in all sorts of products. So it's a very important polymer. But one thing we want to know about, let's go ahead and get its molecular weight just from this. CH2C. So this we could write, see how many total we could write. C altogether 7. H8. Sorry, that was dumb. There we go. C8H8. So what's the molecular weight of that? Okay, so we're going to call molecular weights when we just have one of these things. we're going to wind up calling those M0, M sub 0. So that molecular weight is going to be 8 times for carbon, 12.01 grams per mole, plus 8 times 1.008 for the hydrogen. And to a pretty decent approximation, that's 104 grams per mole. Okay. So that's actually a useful number. We'll come back and see that number later on. I guess I should just mention that if you go with these sort of simple, like a simple formula structure, C3H6O, there could be a lot of different ones, right? I guess this is propionaldehyde or something like that. It's an aldehyde of some kind. Okay, and there are various ways to skin that cat and come up with C3H6O. So if I look in the Handbook of Chemistry and Physics, I find at least 6 different C3H6Os. So you really have to get beyond that. You have to be able to understand this sort of structure, and you have to know. You have to be able to get that from there. Okay. So stick structures, because we don't like to draw the carbons all the time, I'm just going to put the most important one up here right now. I'll put up a regular just like we had. I'll put styrene again. So we'll put in styrene and we'll show everything it's got. So let's see, if to check here, every carbon has 2, 4, 6, 8 electrons. 2, 4, 6, 8 there. They all have octet electrons. The hydrogens all have 2 electrons, so it's a valid structure. It's just a bit much to write. So what we usually write for styrene is this instead. Actually, I don't like how I started out. Let's see if I can be a little neater. Maybe. Okay, let's see. We could do that. And it doesn't show any of the hydrogens. And where there's a carbon, it doesn't show the carbons explicitly either. If it just ends, like if I go, get a different color here, if I go right there, I know there's a carbon there, okay? Because I just do it. That's just the chemistry. So it gets tedious to draw all the carbons, and it gets even more tedious to draw the hydrogens. So that is also a stick structure for start. This shows a few of these things. I guess this one is, none of these are really in total stick structures, I guess. Each of these is a different thing. This should be acetone. Okay. And you can see that you can draw to try to indicate the 3D perspective. This drawer, he likes to, or she, likes to have two things coming out at you by varying degrees, and if two are coming out, then one is going away. So I don't like this. I like to draw these this way, but this is pretty common that people draw it that way. Okay. So then we have the line structure, then we have shorthand, and then we have this. So you've got to be able to be conversant back and forth here, at least for simple structures. So typical kind of problem that would, be fair game on an exam. This is fair game. Although I don't think we would pick this. We would pick something that has a chance of being a material. This is astaxanthin. It's the stuff that makes the lobsters colored. And they go from, this is supposed to be an arrow here. I don't know what happened to my arrow. When you cook them, they turn red, and that's because this astaxanthin changes color on heating. So a typical question is, compute so some of you are probably taught right, and will want to say tis, molar mass. Okay, so I don't really care about the difference. To me, it doesn't matter. The hill of beans of that thing. So you have to be able to look at the whole structure and figure out what there is. And just to do one, for example, this little dot up here, since there's no hydrogen, that's a carbon, and it can't be uncovered. Can't just be out there on its own. It must be a methyl. Methyl is what we call CH3. So there's a methyl group up there. So you have to include all those. And every carbon has 4 of something bonded to it. So this particular one down here is it's just got bonds. Okay, it goes off in this direction to another CH3. I don't need that arrow. It just, here is another CH3. There's really no point in drawing them out all the time. And then, it's got no hydrogen there because it's got 4 bonds already. 1, 2, 3, 4. Now, those double bonds are special. They are a little different than the other bonds. But they still count. Okay. This is solvent orange R, solvent dye. So very important for textile industry is various dyes, and one of the ways that we make them is just to add molecules like this. I haven't been a stickler for dimensions here. I haven't been talking too much about dimensions, but you can figure most of these bonds are on the range of 0.1 nanometers, typical bond. Just try a pen trick here. One angstrom or 0.1 nanometers. Okay, so they're actually a little bigger than that, most of them. Carbon, carbon. about 1.5 angstroms. Okay, but that's why we like angstroms. We can say words like 1 and 2 instead of 0.1 and 0.2. Here's another one. You can just try to calculate the molar mass of this guy. What is the molar mass of this guy? Again, it's sort of a stick structure. Here is right here where I'm drawing in blue. There's a carbon there. It has 1, 2, 3 bonds. It can't have just 3. It must have something, so there has to be an H there. That's how this works. So see if you can't come out with the molecular weight of this particular green, which is called green 3. It's my favorite green. And you can, Google yourself the answer later on. You might find yourself off a little bit from the Google answer because sometimes they may give you this covered with sodium. They don't want to give you just the anion, so there'll be like a trisodium green 3. If they give you the acid form, you would get a different answer than if they do that. Okay, so if they give you the acid form, you replace all those sodiums with protons. This is a molecule that is used in liquid crystal production, C18H19N, and Lord knows how many different C18H19Ns there are. Lots of different choices to put those atoms together in different kinds of molecules. I'm sure there's dozens, if not hundreds of them. But this is an important molecule, and again, you can try to figure out the molar mass of that thing. This time they didn't show you these 2 dots on that nitrogen. Okay, so this is a cyano type arrangement, C triple bond to N, and they just don't show you these lone pairs, but they're there. So another kind of question would be, how many lone pairs are there on that molecule after you put all the hydrogens in and everything else? How many lone pairs are hanging out? Okay, so practical and scientific motivation for doing this. We've forgotten that shapes like I'm showing you here, this simple gas can, stuff like that just didn't exist before polymers. It's not easy to make stuff like that. The way that's made is either blow molding or shaker mill, probably blow molding, with a pinch off at the middle. And we'll see some of those. I'll show you some of those things. There's a school for making milk cartons in the city where I live, Baton Rouge, right now. I've decamped to Baton Rouge from Atlanta. And there's a school for how to make milk cartons, believe it or not, and it's run by ExxonMobil. But these shapes just did not exist. And if you look at all the things that you have around you, from sippy cups right to little plastic pens, all that was made in some other way before the advent of polymers, which happened sort of in the 1940s. So, World War II kind of marks the real ascendancy of polymers. And after World War II was over, oh my gosh, it really took off. Okay. They have other advantages. They never rust. They're quite inexpensive. They're just made out of oil. So, it's kind of ironic that it made that one as a gas can meant to hold oil, but, it's fine. Before that, I can remember gas cans. You might even still be able to buy them. I don't really know. That were made of metal. Oh my gosh, they would rust, and then the gasoline would start to leak. The rust from the gasoline would get into your carburetor, into your fuel injection line. So I mean, it's a big deal. From a scientific point of view, they pose the most amazing physics problems. One of those is the self-avoiding walk. At least 3 Nobel laureates have worked on that problem. And they basically have it now. You basically understand that. Self-avoiding walk is I start off here, and let's say I've had a little bit too much to drink, which I shouldn't have done, but I did it. So I go this way, and then I randomly step in that direction, and then I randomly step in this direction, and randomly step, oops, hopefully that'll go away. You know what, that's kind of hard to do. There we go. Okay, so a real random walk that is not self-avoiding would let me go back in this direction here, right? But a self-avoiding walk can't do that. It can't go back on itself. Okay, and so the self-avoiding walk is sort of like going on a Sunday drive with my wife, because she will say, no, we already went there. Do not go there again. I don't want them to think that we're watching what they're doing. I said, well, they don't care. So, no, you got to go home a different way. So it's somehow up to me to figure out how to get back. And you can see I'm going to go a longer distance. So this real polymer chains are kind of put together like that, believe it or not. These little dots represent our monomer units, and these little lines will represent our beads, will represent bonds. And so there's a whole area of polymer physics. That goes into this study. So part of the platypus is a chemist, it's a physicist, it's an engineer of various kinds. That's what takes material science into platypus land. Right now, we are faced with applying everything we can about polymer chemistry and polymer physics to solve this incredible environmental problem. How do we get rid of this stuff? It's really... later I'll have some statistics about that. Or maybe is a problem for you all. And you can read this UN report here about it to get an idea, but it's a serious problem. Industry wants to solve it because their very existence depends on it, and most of us want to solve it because we just don't want a junky environment. All right, polymers, let's use that mer word again. Many, that's parts. Poly means many. So it's something made of many parts. The basic building block of polyethylene, the gas can that you looked at was probably polypropylene, but it's a close relative of polyethylene. We use polyethylene in garbage bags, for example. In polyethylene, our basic building block is ethylene. So this is ethylene. ENE signifies a double bond. Okay. So that's kind of the... this is sort of a weird... Say, okay, let's take some electrons. There's really 4 electrons on these 2 bonds. There's 2 bonds there. And see, now he's drawn with... he's taken 2 of them and put them on other sides of the carbon, then he's going to link those together and do that repeatedly and make polyethylene chains. Okay? So if you just did that, you would have pure polyethylene. That's called a linear polyethylene. And it would be a crystalline material difficult to handle and deal with. So in fact, and also the chemistry works a little better, I think, with some other monomers that give us ethylene-like behavior. So we'll talk about that eventually. All right, so I'm going to stop again here and take a little break.